and that's actually what our last speaker will talk about the parameterization of hyperparameters. And I'm happy that Sylvain Robert will talk about it. So he has a background in environmental science, but moved in master and PhD in the deep statistics, and now he is working for SwissRe as a data scientist and addressing a really nice topic. So it's you.
Thank you, Hai, for the introduction. Okay, and hi everyone, and I'm going to speak a bit about some work I've done on landslide modeling at SwissRe. It's a joint work with Michael Evel, Thomas Phillips, and Klaus Brünniger, who are maybe online right now, I don't know. Let me just, yeah. I'll give you a bit of business context to just give you an idea of why at SwissRe we care about landslide risk. Don't worry, it's not a sales pitch, right? So I'll keep that short and then dive into the methodology, and in particular explain to you a bit how we develop a new model, which is a lot about landslide runout, as you will see, and how we use Bayesian optimization to optimize the parameters. So just to keep your expectation, there is nothing about deep learning, about advanced machine learning techniques. It's a link with machine learning in the series is really about this Bayesian optimization application to learn the parameters. It's more about having a physical model that then use data to inform about the parameter. And then finally, I'll show you some results and how the new landslide risk map we develop actually help to estimate better the landslide risk. So quickly on that, SwissRe is a major reinsurance company, like probably you know, or if you don't, it's okay. And a large share of our business is on natural catastrophe reinsurance. So we reinsure insurance company, but also state entities like an entire country or maybe a municipality against natural catastrophe events, things like hurricanes, floods, earthquake, and so on. And a rising trend in reinsurance, or a rising worry, if you prefer, has been about so-called secondary peril. So the usual type of natural catastrophe is earthquake and hurricane, that are major financial losses. But more and more in the recent years, there have been rising to damage due to drought, to floods, to wildfires, as we see in the news regularly, and also landslides. Hence, the reason to improve our view on all of this risk, and today a bit more specifically, and on landslides. So one thing that we provide as a reinsurance is a online service for natural catastrophe risk, and one of the layers that we have is a layer of landslide risk. And you can imagine two use cases. So clients, maybe an insurance company that wants to have a fine view of landslide risk in different locations to price differently homeowner insurance, for example. Or you can imagine also clients can be an organization. For example, we have the Red Cross using our service that use the maps to inform itself about risk on the ground and maybe optimize operation. Why don't build a camp where there is a high landslide risk or a high earthquake risk. So these are two typical use cases of the map we are offering and building. That was it for the context. Now, as promised, I kept it short. Now I'll dive into the methodology. So we are not, I mean, SwissRe is a generalist company where we do all kinds of risk. So we have maybe a simplistic view on landslide. I'm sure some of you in the audience actually know much more than I do. But the way we look at landslide, we split into two kinds of risk. So we look at the susceptibility risk, which is the risk at any given location of a landslide starting there, and the runout risk, which is the risk of a landslide hitting a given place, but probably starting higher up, right? And you can imagine from an insurance perspective, the runout risk is really what matters, right? Because very often your assets, houses, roads, people are sitting at the bottom of the slope, not in the middle of the slope. Right? Here you have a road, maybe, but the main damage is made at the bottom. So it's very important that we have a model that can capture that. And this is one part that was missing until now. Right? So to give you a big picture on the process, so our input is all kinds of information about the topology. So things about the slope, the geology underneath, the earthquake risk, the rainfall risk, and so on. And then from that, we build a susceptibility map. So this risk of a landslide starting in a given place. This was done already before by Emmanuel Buchy. It's very useful, but it doesn't give the whole picture, right? And what we do is that we take now that as an input and build model, runout model that tries to emulate what will happen if landslide starts a bit everywhere on this slope, and what is the risk then at the everywhere, right? Especially at the bottom of the valley and the slope and so on. And you have different ways to approach this, right? But the most natural, or I mean, depends on your background, right? But from a physical point of view, would be to try to model the physics and look at your detachment area, and you try to identify them in the landscape, and then you model how much ground there is available, what is the land cover, right? Is it rocks, is it soil? And then you could try from that to simulate the physics of how the landslide is moving downhill, right? But it's not really feasible for us because, one, we want to do it on a global scale. So we don't have this data available at high resolution everywhere on the globe. And second, it will take a lot of computational resources, right, to run all this landslide everywhere. So we came up with a kind of pseudo-physics approach. I call it. Imitates a little bit the physics. So it takes the susceptibility map as a starting point, and then it tries to simulate how the risk propagates downhill following the slope, right? But with a very simplified physics that depends on a few parameters, like how much the slope influence, how much momentum we allow, how much you need to overflow on some obstacles, and so on. If you do that, you really see the picture of the landslide starting and moving downhill. And that's where the core of the talk enter, right? So we have these parameters, like I say, the amount of slope influence and so on, but we don't know what value to give to them, right? It's just a kind of a pseudo-physics. I cannot really derive them from physical principles. So I'm a statistician by training, so I think about it as, oh, okay, can we use data to learn about it? And we try to build training data sets to try to inform us. So we look at many landslides, many 120 landslides that we could find the exact or more or less exact polygon of where the landslide occurred, and then from that we created points that are within and without the landslide area, and then use that to apply our runout model, and then see how well we separate between two classes, right? How well we predict the risk on the landslide point and on the non-landslide point. So it's back to familiar ground, right? We have a score, maybe AUC or accuracy or whatever, and then we just need to optimize it. Thing is that it's not the usual function in deep learning or whatever, or ordinary least square, where everything is differentiable, and you can just make the information flow back from the score. You take the derivative, and then you get the best information about your parameter, right? And you can find your optimum, being a global, local optimum, doesn't matter. We cannot do that because our runout model is a kind of black box, right? Physics that run many iterations and so on. So it's much more complex. Furthermore, it's also expensive to compute, right? Every time you try to run the simulation at a given set of parameters, you have to simulate all this landslide and so on. So that's where we enter Bayesian optimization, right? Which is now, I don't know how much detail I want to give you, but it's a general method that allows you to optimize a function that has this property that is expensive to evaluate, that is not differentiable, but about which you can make some assumption of smoothness over the parameter space that you're interested in estimating. Maybe I'll jump straight to the illustration of it. So the way it works here, imagine you have a one-dimensional parameter on the x-axis, and you're trying to find the maximum of the objective function. In this case, the dotted line. We know the truth. And you start with a non-informative Gaussian processes prior. So it's a prior over space of function, right? So imagine it gives you many possible functions, more or less smooth in this space that could be your objective function. You don't know which one. And then you start to sample the space of parameter, right? So you try a given parameter value, with a given number of steps and diffusion parameter and so on. And you test the simulation and you see what is the result. And then you do it in some other place. And as you do that, you learn more and more about the underlying objective function. And now the key aspect of Bayesian optimization is to know which next point to try out, right? Like which other parameter to test. And here, this is embodied in the acquisition function, which makes a trade-off between exploration and exploitation. Right? If you could randomly sample the space, but it's kind of wasteful, right? Think about it as it's expensive to query, so you don't want to waste points on any kind of parameter value. You want to focus on the promising area, but at the same time, you still want to explore a little bit. And there are some criteria where you choose not the highest mean value, but the highest upper quantile, right? So you kind of optimistic look at where there is uncertainty, and I think that maybe it can be a good guess, right? So that's the point that you try to query. Applying this methodology to our problem, so we have a parameter space of about 9 dimensions. We have things like the amount of flow, the dispersion rate, the momentum strength, and so on. And here's just an example of some slices of this space, this function that we try to estimate. Each point is function evaluation, right? So one set of parameters that we tried and computed, and then the color is the score, right? So how well it performed in terms of classification. And you see how the algorithm doesn't go too much where the score is low, and then it focuses much more on areas where the score indeed was better and promising, right? So it's moving slowly, but also exploring. And you can see here on two different slices, two-dimensional slices. But you have to imagine it's a hypercube, right? In 9, 10 dimensions. So you cannot do an easy grid search, and that's why it makes sense to use this optimization algorithm. So we put all that in practice, and then we get our new runout model, and now we want to illustrate how it works and what are the results improvements. This is a valley in Graubünden. You recognize a Kur there, and it's known to have some landslide risk. If you look at the original map that we produced with the susceptibility risk, so the risk of having a landslide being triggered in a given area, you get this very high risk on top of the slope, or let's say where the slope is the steepest. But at the bottom, it seems that, oh, it's pretty safe, right? You can build a house just there. Even so, common sense will tell you it's not a good idea. And if we run now our runout model, you can see that it really captures well this topography and really shows how the landslide can spill down and really go over the border of the valley and so on. This is another example where we have an actual landslide that occurred in 2017 in Sichuan. It's an area prone to many landslides. Many houses destroyed, people dying, and a road and a river blocked. This is on Google Earth, just a footprint of the landslide. It was not used for training. And here you can see the map. So try to imagine the water here. So again, the susceptibility risk would be high on the slope, but very low at the bottom, say, oh, it's pretty safe to build a road there. But again, we know it's not true, right? And our runout model exactly says that indeed, this is a very risky area to put any kind of road or houses, and maybe either you should price it more as an insurance company, or you should consider to put some protective measures like whatever, some walls or anything that can prevent the landslide. This is another example. I'll just go quickly. In Canada, Mount Meager, a very major landslide, 7 kilometers long, well, with some mud flow and so on. You can see the footprint again on Google Earth, and then the susceptibility, as usual, doesn't capture well the whole spread of the landslide. It tells you that it's all fine. And here we can see with the runout model, it does capture well. Here we see that it doesn't go far enough, right? The actual landslide went all the way there, and here we'll say it's safe. I think it's partly unavoidable, right? It's a very catastrophic event. We cannot capture all these risks, otherwise we'll end up saying that too many areas are high risk of landslide, right? It's a question a bit of how far in the tail do you want to go and capture the risk for. But it's good to understand also that there are some limitations with this method. That's it, just a few words of conclusion. We developed this new runout model for going beyond susceptibility risk mapping. We develop a pseudo-physical model for that. We use Bayesian optimization to train the free parameters of the model by mapping the problem to a kind of classification problem, and then using Bayesian optimization to simply optimize back. And putting that together, we produce a new landslide risk map, global coverage, 30 meter by 30 meter resolution, which is not so high compared to applications we've seen before, but for our standard, and if you think about insuring houses, it's pretty accurate enough. And we now have not just a susceptibility, but also runout risk provided for our clients. Thank you. I don't know if we have time for questions now, otherwise in the chat afterwards. I'm happy to take any question.
Thanks a lot for this inspiring talk. It's really interesting because you also close the round actually from data über models and algorithms to a deep understanding of processes, because otherwise you cannot produce a runout model if you not really understand how processes in our environment are actually happen. And also the application, we started from a global application from tools, and now we end with a global product or with a global applicable product again. Thanks a lot. So questions in the upper